of the wind. Here's a small wind turbine capable of producing 1.7 kilowatts. That's a little bit over 2 horsepower. It's got a blade diameter of 6 feet. As you can see, it really gets moving. It looks like it's going slow and changing directions on the camera because of a physical phenomenon known as aliasing. It has to do with the refresh rate of the camera as well as your eye's ability. Before I tell you about the process of converting bad power created by the wind turbine into good power, which is usable in consumer electronics, I'm going to tell you a little bit about the green room. The green room is actually my bedroom. Yeah, kind of messy. But the idea behind this green room is to have every consumer electronic device powerable by a renewable energy source. In my case, it's wind power. Right now we're looking out the window of the green room at the wind turbine. Now, the electrical power created outside by the wind turbine is what an electrical engineer would refer to as bad power. It has a variable frequency and a variable magnitude. What happens inside the green room is that this bad power is turned into good power, which has a constant frequency and a constant magnitude. To illustrate the difference between bad power and good power, I've drawn up a little diagram. First thing you'll see here is the bad power. Now, power is composed of voltage and current. It's actually the product of voltage and current. That's a law. And what you'll see here is that bad power is very messy compared to good power. To help simplify this a little bit, you look at the high wind speed. This is the voltage signal that you would get off of the wind turbine during a high wind speed period. There's a high frequency. That means the voltage is changing polarity very quickly. And as the wind slows down, the frequency decreases and the amplitude decreases. Now, if you're going to hook up a common consumer electric device to this wind turbine, the only usable power would be at about 60 hertz, and that might only occur for a short period of time while the wind is at just the right speed. And also the amplitude would probably not be correct. So what happens in the green room is we convert the bad power into good power. Here's a voltage waveform of common good power. The amplitude is 120 volts, peak to peak would be about 240, and it has a frequency of 60 hertz. Now, once the power has been transmitted into the green room, there's a 3-step process from turning it from bad power, coming directly from the AC transmission line or extension cord, into good power, which I can use on a lamp or an alarm clock. Okay, the first step in this process is the inverter. This device is a full-wave bridge rectifier. By the way, the Fresca can that it's sitting on is acting as a heatsink. An inverter. This is a full-wave bridge rectifier, which can take an AC signal, which means it has a varying polarity and a varying frequency, and convert it into a voltage signal that has no frequency, or zero frequency, and the polarity does not change. The next step in the process are these DC batteries, which can store power, which is a very handy thing to do, and there's no way to store AC power. So this is a very critical step. The stored power, DC power, or DC voltage, is then transmitted over to the other inverter, which converts DC to AC. You put 12 volt DC into this black box, and what comes out is beautiful 90, the magnitude is about 90 volts and the frequency is about 60 hertz. And from this you can plug in any common consumer item like a desk lamp, and these devices will function just as though they were being powered by a wall outlet. What we have here is a 3D computer model of the wind turbine. I drew this up and designed it before I began building the wind turbine, which is always a good idea. There are four main components here. The black components are structural, and I won't be talking about them. The first components are the blades. They are very critical. They have to be very well balanced, well shaped, and they have very specific shapes that they have to be to get the correct torque and speed out of them. The reason the speed is important is because the frequency of the voltage generated is dependent on the speed of the blades. I'll show you why here in a second. What I'm zooming in on is the actual generator, which I built by hand. The green circles here represent magnets. These are very strong rare earth magnets, which cost about $120. Seems a lot when you're on a college budget. And next to it, you have the coils, which I am showing in pink or light purple. The blue and red lines you see between them are representing magnetic flux. Now, if you've had a physics course, you'll immediately understand how a set of magnets spinning rapidly past a coil will create a voltage. I'm not going to go into how that works, but you'll just have to take my word for it that it works. Back here, this blue part is a hub that actually came off a 91 Toyota Corolla, I believe, and I got it out of junkyard for free, so I was pretty pleased with that. But that is really the only moving part on the wind turbine, and it was designed for automobile or high stress use, so it works very well. The only other moving parts on this wind turbine are the magnets, which are attached directly to the blades.